So now we are in chapter 2, section 2.1, derivatives and rate of change. Often Calc 1 is called differential calculus, and we do have other pieces to it for sure, especially in the beginning and the end, but a huge chunk of it is the idea of derivatives and doing differentiation. So let's take ourselves back to a little bit earlier in the semester, even though it hasn't been that long. And when we talked about tangents and we talked about velocity. So take a look at this function here. We have this nice curved function. And then we have, if you recall, this is a secant line. We have 2 points, a f of a and x f of x. And so what we're being asked to do here is just find the slope of the secant line. And so we just need the slope of that line. And as we know, we have 2 points on that line. And we know that the slope of any line is, typically written as y2, y1 over x2 minus x1. That's your typical slope just from back in the day. It's no different here. We just have some different notation for the values. So we can say f of x minus f of a over x minus a. So that would be the slope of that secant line. Okay, slope of the secant line. Right here. Okay, so it's the slope of that line. But what we talked about before was, what if we wanted to know the slope of the tangent lines? Remember, if there was a line that was just touching that function at one point, so that line was touching the function just at one point, not going through 2 points, but just touching that function at one point, what would be the slope of that line? And that's really the big idea that we're going to be talking about. So the tangent line to the curve of this function at a point is a line that contains that point and has this slope. Notice it's the exact same thing we just found, except it uses the idea of a limit. And that's because what's happening is you're looking at what happens is the distance between those 2 points on the secant line get closer and closer and closer and closer and closer and closer, because basically they get infinitely close to one another, and now you just have 1 point, and that is where that line is touching the function. So this is true provided that the limit exists, and the value of this slope is also, another way we can say it, is that it is the slope of the curve at x equals a. So again, it is just on the curve 1 point. Let's take a look at an example. So we have, find the equation of the line tangent to x cubed at x equals 1. So first what we'll do is we'll draw a point at x equals 1. So we notice we're at the point 1, 1 here. And the idea is we want to find, and again, you know me and my tablet, we do the best job we can to do a tangent line at x equals 1. So we're just touching at 1 point. And we want to know what is the slope of that line, because that is the slope at x equals 1 on x cubed, y equals x cubed. So when it says equation of the line, you want to take yourself back. Remember, there's just 2 things you need for the equation of a line. You need a point on the line, and you can see we have a point on that line, and that point, not surprisingly, is 1, 1. That's our point. And of course, we need the slope of that line. With those 2 things, we can find the equation of this line that I've written in red. So we need the slope. Well, what we just learned was that the slope is the limit as x goes to a of f of x minus f of a over x minus a. So in this case, what we want to think about is f of x is our function, and f of a and a are the relationship to that point. They are that point. So now we can just plug in what we have, which is the limit as x goes to a of f of x. Well, that is our function here, so don't forget that I could write this just as easily as f of x equals x cubed minus, and then f of a is just f of 1. So coming down here, we see that that's the same as 1 cubed, which equals 1. We already knew this because we have our point here, so it's just 1. And then we divide that by x minus a. And because that point is 1, 1, you want to think about the fact that your a is 1. So x minus 1. Now, one thing that I should do, just I can add one more thing in here, not surprisingly. We don't need that a because we just talked about the fact that that a is 1, so let's just replace that. And this is what we need to find the limit of. But we've done some limit work, I'm sure you recall, and what we have found with our limit work is that if we were to just plug in 1, which is what we should always do first, when we take a limit, is that we would get this idea of 0 over 0. So by plugging it in, we get 0 over 0. That's a problem. Okay? That's not a slope because it's not a real number. So what we need to do is, and this is one of the common things, we did see an example of this in our notes earlier, is we should see if this factors. And this takes students kind of back to their algebra days. But this numerator factors. It is the difference of cubes. If you remember, it's the difference of cubes. So if you want, you can pause. You can find the difference of cubes if you need to Google it, or if you remember it, go ahead and factor and then come back. But the difference of cubes is because the first term is something cubed and the second term is something cubed. It's not exciting. It's just 1 cubed, which is 1, but it is something cubed. So if we want to factor the numerator, that's going to be x minus 1 times x squared plus x plus 1. So if we were to multiply that out, we'd get x cubed minus 1. And then in our denominator, x minus 1. Not too surprising here, what you should notice is we have that factor of x minus 1 that simplifies. The reason that that's really important, of course, is because it allows us to no longer have that issue of 1 in the numerator and 1 in the denominator. That's going to give you the 0 and the 0 when you plug in x being 1. But because we got rid of that factor, which was the issue, we now have this. And when we plug in 1 here, you can see that we get 1 squared plus 1 plus 1. And that's just 3. So taking ourselves back to that was great. We did a great job here. What we have now found is that we have the slope at that point at 1, 1, and we have the point 1, 1. So we have the two things we need to find the equation of a line. So now you take yourself back to your algebra skills and you remind yourself that you can find the equation of the line by doing it does not look like an N. So our line is going to be y minus 1 equals 3 x minus 1. So I'm using point slope form here. And that's going to give me y minus 1 equals 3x minus 3. And then just spacing wise, I'm going to bring it over here. Y equals 3x minus 2. So that is the equation. What we have found, pretty exciting, is that is the equation of that line. That is the line that is tangent to x cubed at the point x equals 1. And that's the equation of that line. So that's a big deal. But that is our final answer in kind of a 3-step process there. So make sure you recognize that. That's going to be a pretty common thing to do. Now, what you want to see is if instead of x, I wrote a plus h, okay? If I wrote a plus h, so I just replaced x with a plus h in the two places that I have x, notice that it becomes this, which then becomes this. And this is just an equivalent way to write what we just did. So we have this one limit as x goes to a. Notice if we do the limit down here just changes well. As a plus h goes to a, that means that h is getting smaller. Because if you have a and you have a plus h, and a plus h is going to a, it's like this. So h is the difference between the two, the distance between the two, and h is going to 0. So that means that a plus h is approaching a. You'll see more. Okay, so now, page number 2. We have a position function, s equals f of t. That is the position of an object at time t. So now we're kind of talking about like a real world situation here. If we have a position function, Then the instantaneous velocity, remember we talked about average velocity in the past, but if we want to talk about instantaneous velocity, we're trying to find the velocity at one point, not over an interval of time. So that instantaneous velocity at time A, as you can see, just trying to find my pointer here, there we go. I don't know, I think you guys see an arrow, but I see just a tiny little dot. The instantaneous velocity of the object at time A is given by this. I want you to see that it is very, very similar to the other two examples that we've seen. It's just in the first piece here, notice that instead of x, we have t, and that this is what we saw, we just saw. And so these are all like equivalent expressions for what we're trying to do here. So let's look at an example. We have a function, it's a position function, they tell us. It's an equation of motion, t minutes, and s is in meters. So minutes and meters. Let 10 a.m. correspond to t equals 0. So when no time has passed, it's 10 o'clock. And then our question is, what is the instantaneous velocity at 10:05 a.m.? So because t is in minutes, and because t equals 0 is 10 a.m., how many minutes is 10:05 a.m.? T equals 5. Okay, so what we're trying to find here basically is v of 5. What is the velocity at 5 minutes? But that's given to us at the top there. Notice it's given us at the top. So really what we have is the limit as t approaches 5 of f of t, that's given to us in the problem, 6t squared plus t plus 8, minus f of a. So now it's saying what would happen if we plugged in 5. So f of 5, that's going to be 6 times 5 squared plus 5 plus 8. So we evaluate that. That's just a value that we need. If you do that, it's pretty big, as you can imagine. It's actually 163. So we're going to subtract 163. Oh my gosh, 163. And then notice that we're going to divide it by t minus a. So think about what that's going to be. T minus 5. And then we just evaluate this limit, and that is the instantaneous velocity by definition from above. So we have limit as t approaches 5. Now we have 6t squared plus t plus 8 minus 163. So we should do that. That's what I should have done. Ready for that. Ready. So combine those two terms. You should get minus 155 over t minus 5. Now, you probably have not done this recently, but it does factor. It's just kind of a more difficult trinomial there in the numerator now. And what I want you to see a couple things is if you were to plug in 5, you will get 0 in the numerator and you will get 0 in the denominator. And that should tell you, because you have a polynomial divided by a binomial, that you have some sort of, the 0 over 0 factor means that you have some sort of hole that you need to get rid of. And so you would want to guess, the best guess here would be, I need to get rid of that t minus 5 or I'm not going to be able to take this limit. So I'm going to guess that there is a factor of t minus 5 in my numerator. And by doing that, you can now kind of figure out the other part of this factoring situation, because if in fact it is t minus 5, then this is going to be 6t, and then we have a positive there and a minus 155, so we're going to guess that it's a plus, and 5 times what gives us 155? That's going to be 31, and then you can multiply it out if you want and double check, but that's going to give you the 6t squared, plus t minus 155. But more importantly, what it does is it allows us to factor out that t minus 5, to simplify that t minus 5 at this point. So we have the limit as t goes to 5 of 6t plus 31. So go ahead and plug that in and see what you get. And you should get, when you plug it in, 61. And that's going to be probably not surprising to you. It's a velocity. So notice we're talking about velocity. Velocity is speed, that sort of thing. And, you know, like we drive miles per hour, that's a velocity. And so in this case, we have meters per minute. And that's how fast this function is going. It's a position of an object, how fast this object is going at 5 minutes, exactly at 5 minutes, because it's instantaneous. Okay. All right, so now we have the same thing again. So this is now the definition of a derivative. The derivative is what we've just been looking at. So take a look and notice there's these limits we've seen already and used a couple of them already. This is the notation. So it is, we say f prime, that's just quotes, f prime of a. That's how we read that, f prime of a. And it's, by definition, the derivative of a function at a point, meaning the slope of the line that is tangent to that function at that point. All the ways to say that, and that is the definition of it as long as the limit exists. Because it's a limit, it has to exist. So a few notes about this is, like we already saw this example, we found a tangent line to a curve at a point. And notice this looks very similar to what we found for that x cubed function. So it's just telling us what we already know, which is that this is the equation of that line. If you find the slope and you have a point, you can find the equation of the tangent line. We've also found instantaneous velocity. We just did that. And in order to do that, we did find the derivative at a point, and that's what we found. Okay, so it's just telling us, okay, you can use that notation, because we didn't use that notation yet, but you can use that notation. And in general, the rate of change of a function, so if you have a function, the rate of change with respect to x, which just means that the function is a function of x, at some certain point is f prime of a. Okay? So it's all about the rate of change, which is the big idea of the beginning of calculus. So let's take a look at an example. Find f prime of a if f of x equals the square root of x plus 1. And all this is asking us to do is take that definition, f prime of a equals the limit as x approaches a, and then we just need to do f of x minus f of a over x minus a. Now, here is a hint for you. As we do this, we are going to keep our x's and our a's. And so that's kind of a key thing to see, is that those are going to stay in this because we're not given a certain point here. We're not given at some value, x equals 1, x equals 5, whatever. We're just told find f prime of a. So that means our ending values will have a's in them once we take that limit. So the setup is the limit as x approaches a, and then we just put f of x, square root of x plus 1. Then we subtract just what happens when we plug in a. And notice the square root of x plus 1, when you plug in a, the square root of a plus 1. So it looks like that. Notice the parentheses because I have to subtract it. And then in the denominator, exactly what we have, x minus a. There you go. What you'll notice in the numerator, which is going to be really helpful to us, is that our denominator, nothing really exciting happens, x minus a. But in the numerator, we have square root of x plus 1 minus the square root of a minus 1. So we have a plus 1 and a minus 1, and so that ends up giving us just the square root of x minus the square root of a. And what you might be thinking now, I don't know, but hopefully, maybe you're thinking about the fact that the last time we did a limit with a square root, it was only one square root that time, but the last time we did it, we used the conjugate. in order to simplify. Because right now, as x approaches a, if you were to plug in a, because that's what you're trying to approach, if you were to plug in a, you're going to get 0 over 0. And we know that's a problem. But we also know that the most common way to fix that is by using the conjugate. So that's what we're going to do. We're going to use the conjugate and see what happens. And I'll tell you, it's good stuff. So the whole idea here is to rid ourselves of the root. So we're going to multiply by that numerator. Sometimes the conjugate, it can help to multiply by the denominator. That's not going to help here because we don't have roots in the denominator, but we're going to multiply top and bottom by the conjugate, meaning, of course, the same exact thing, but opposite sign of the numerator. So I go like this and go like this. Okay, I'm going to come back over here just for spacing. So notice, as always, the whole big idea behind the conjugate is that we have the opposite sign, so this is the difference of squares. So even though it's 4 things that are getting multiplied, the middle term simplified is 0. So when we do the square root of x times the square root of x, we just get, where am I? my little pen. Why do you do this to me? There we go. I see it. It's so teeny. The square root of x times the square root of x. So let me put back my limit. Never forget your limit. Never forget it. Because we haven't taken the limit yet. Haven't taken it. So the square root of x times the square root of x is the square root of x squared, or just x. Then you have the square root of x times the square root of a, square root of x times a. But then you have minus the square root of a times the square root of x, minus square root x times a. That's 0. Then you have minus the square root of a times the square root of a. So that's minus the square root of a squared, or just a. Whew. Okay, now we have x minus a and the square root of x plus the square root of a. So yeah, nothing exciting happened there, but that's okay because we have big excitement in our numerator. Our numerator has a binomial that simplifies with the binomial in the denominator. So simplify, simplify. Don't forget that does not mean there's nothing in that numerator. You still have a factor of 1 that you have to think about. I mean, it's not that there's nothing there. But then that leaves us with the square root of, technically the square root of x. Doesn't really matter because they are being added, so there's no difference which one I put first, but I will be consistent. So the square root of x plus the square root of a. And now what you should notice is that when we take that limit, which involves us plugging in a, we are going to now get something that is not 0 over 0. We get 1 over the square root of a plus the square root of a. And that gives us 1 over 2 times the square root of a. And that is our answer here. They want f prime of a. So this is f prime of a. This is f prime of a. I know that there's a lot of work in between them, and we got to know what it is, and we got to show it. But f prime of a is 1 over 2 times the square root of a. And the bigger idea behind that, which is what we'll see in the future here, is that it means that if you were given a point, so instead of being just told a, if you were given a point, x equals 1, x equals 5, x equals 10, all you'd have to do is plug that in for a right now, and you'd have the derivative at that value. So what I want you to see is this is the more general form of the derivative, one example of the more general form of the derivative, because it allows you to plug in any value for a and find the slope of the tangent line at that point. Okay, last example here. If you know that the derivative of a function at a point a was this, so hey, don't even have to do the work. We already have the derivative at a. It's given to us. It was done for us. Find the equation of the tangent line at the point 1, 2. So we just want the tangent line here. We've already done this. We need 2 things to find the equation of any line. We have a point that we need, staring us right in the face. There it is. And we also need the slope. But the slope was already found for us because that is the derivative. So we have f prime of a equaling negative 2 over a squared. But we know what our a is in this case. A is the x value of our point, and that is 1. So all we need to do is plug in 1, see what happens. You can just evaluate it. So we have negative 2 over 1 squared. Yeah, we get negative 2. And then now we have everything we need to find the equation of the line. Okay. Point slope form is the way I always go. Some students do like finding, they do y equals mx plus b. They like finding b. That's fine too. So I'm going to do y minus 2 equals negative 2 times x minus 1. That's going to give me y minus 2 equals negative 2x plus 2. And then by adding 2, I get negative 2x plus 4. So, since the question is find the equation of the tangent line, we have now just found the equation of the tangent line. So if you were to graph 2 over x, and you were to look at the point 1, 2, you're going to see, and you graph the line tangent at 1, 2, the equation of that line is negative 2x plus 4. And that is section 2.1.